Hello, everyone joining us. I wish you all a warm welcome to the third ABSL IT Club powered by Authority Partners in 2023. This year's ID Club, we're ending with a very extraordinary fireside chat. We're gonna elevate our testing today and hear more about the power of containerization. And it is my pleasure, before I introduce our guest speakers, Rabina and Aisha, just to quickly remind you on some technical data that we have regarding the ABSL Club standards. So every ABSL Club happening online or in hybrid format is being recorded only for knowledge sharing purpose in the ABSL local and international community. In today's session, you can ask questions in the chat room for the Q&A session that will happen in the end of today's event, and our speakers will just answer the questions by reading them out in the end. And of course, if you have any questions after the presentation, you might write them in the chat room as well. All the questions we don't manage in the given time slot to answer, we'll answer later on via email in cooperation with our guests. And now it is my pleasure to announce our guest speakers today in the fireside chat, Aisha and Rabina. Yesterday when we met, I learned actually that there are not just amazing Q&A engineers at Authority Partners, but also alumnus from the AP Lab, which gives us a completely new dimension regarding expertise being developed in our member companies through years, and people from internship or career development programs actually entering highly driven careers in the companies. So I am beyond excited to hand over the mic to Rabina and Aisha and to expand our collective knowledge in testing and the power of containerization. So Rabina and Aisha, once again, thank you for your time and welcome to the ABSL IT Club by Authority Partners. Enjoy your slot.
Thank you, Adi, for the kind words. Hello, everyone, and welcome. My name is Rabina, and even though Adi did a pretty good job, let's do just a quick round of introduction, a quick get to know me. I've been working with AP for 2 years now. I am a team lead and a QA automation engineer, and something that I never forget to mention, as Adi already said, I am an AP Lab alumni.
And hi, my name is Aisha. And also, as Bina, I am a QA automation engineer working with Authority Partners for the past 4.5 years. And also a shocker, I am also an AP Lab alumni.
Yeah, now that we have those pleasantries out of the way and the intros where you could just switch out the years and name and get essentially the same text, let's start with a brief introduction as we dive into an exciting and transformative topic today, which is containerized test environments. In the fast paced world of IT, staying ahead is not just an option, it's a necessity. Today, we're going to explore how containerization is revolutionizing the way we approach testing and development. So, buckle up, get ready for an enlightening journey, and let's embark on this exploration of containerized test environments together. And I forgot to turn off my camera, so just let me do that real quick. Okay, there we go. We could start off with a simple definition of what containerization actually means. So, containerization is a lightweight, portable, and executable software packaging method that involves bundling an application and its dependencies into a single self contained unit known as a container. Containers provide a consistent and isolated environment, ensuring that an application runs reliably across different computing environments. Now, with that being said, let's go over the general purpose of containerization. Firstly, it enhances consistency. Containerization helps address the common "it works on my machine" issue by ensuring that the development, testing, and production environments are consistent. This consistency minimizes discrepancies between different stages of the software development lifecycle. The second main one is portability. Containers encapsulate everything needed to run an application, including code, runtime, libraries, and system tools. This portability allows applications to run seamlessly across various environments, whether on a developer's laptop, a testing server, or in the cloud. And lastly, we have scalability. Containers facilitate scalability by providing a lightweight and efficient way to deploy and manage applications. Multiple containers can run on a single host, optimizing resource utilization and enabling the easy scaling of applications to meet increased demand. And now that we know what containerization is and what its purpose is, let's do a quick overview of the containerization technologies. I believe most of us have heard of Docker. Docker is a leading containerization platform that has gained widespread adoption in the software development community. Docker provides a set of tools for creating, sharing, and running containers. The key components include Docker Engine for running containers, Docker Compose for building multi-container applications, and Docker Hub for sharing container images. Again, we have to mention the key benefits, and yes, they do reflect the purpose of containerization. Containers offer process isolation, ensuring that an application and all of its dependencies are encapsulated and do not interfere with other applications or the underlying system. Additionally, on the list, we have efficient resource utilization. Containers share the host operating system's kernel, making them lightweight and efficient. And this allows for better utilization of system resources compared to traditional virtual machines. And something very important in our everyday working environments is rapid deployment. Containers can be started, stopped, and deployed rapidly, enabling quick and consistent application deployment. And as we've mentioned, this speed is particularly valuable in dynamic development and deployment scenarios.
Thank you, Rabina, for this quick introduction to today's topic. Now that we know what containers are and what their purpose is, let's briefly go over traditional test environments. We should start by understanding what we mean when we say traditional test environments. So, in a traditional testing environment, the software application is deployed on physical or virtual servers that mirror the production environment as closely as possible. This environment typically includes databases, application servers, network configurations, and other components necessary to simulate the real-world conditions in which the software will operate. Now, one of the immediate challenges we face is resource management. The manual allocation and management of resources can be time-consuming and prone to errors, leading to inefficient resource utilization and potential bottlenecks in our testing workflows. Moving on to dependency management. Ensuring consistencies across different testing environments becomes a challenge. Dependency conflicts and versioning issues can make it tricky to maintain a reliable and reproducible testing environment. Difficulty in managing versions of test environments can make it challenging to revert to a stable state, potentially causing prolonged downtimes. Also, managing consistent configurations across different testing environments can be challenging, leading to configuration drift and difficulties in reproducing issues. Isolation is another key challenge. Achieving true isolation between tests is often difficult, especially when tests share a common environment. This lack of isolation can result in interference between tests, leading to unreliable results. Scaling traditional test environments can be complex, particularly as we deal with the growing number of tests or aim for parallel test execution. This can result in longer test cycles and slower feedback in agile or continuous integration workflows. Now, let's talk about the complexity in managing test data. In traditional environments, handling test data, especially when tests require specific datasets or databases, can be a stumbling block. Inconsistent test data can lead to false positives or negatives. Limited availability of test environments is another issue. In larger teams with competing demands, this can lead to delays in test execution, scheduling conflicts, and challenges in maintaining a consistent testing schedule. We can see that all of these are something that most of us encounter on a daily basis. So now that I've made you pretty much barf on our traditional testing environments, let's put containers into play. Besides what Rabina already mentioned, the major advantages are reproducibility. Container images contain the entire testing environment, including dependencies and configuration. This makes it easy to reproduce the exact same environment across different stages of development, from local development to testing and production. Dependency management. Containers encapsulate dependencies, making it easier to manage and version control them. This eliminates conflicts between different versions of libraries and ensures that the required dependencies are present in the testing environment. Versioning and rollback. So, container images can be versioned, enabling teams to roll back to a specific version of the testing environment if issues are discovered. This helps in maintaining a stable and reliable testing process. Overall, containerized testing environments offer a modern and efficient approach to managing testing infrastructure, addressing many of the challenges associated with traditional test environments. These advantages make containers well suited for contemporary software development practices, particularly in environments adopting agile methodologies and CI/CD pipelines.
Thank you, Aisha. Now that we've covered the basis for this topic, we will move into setting a baseline for our demo. In the following sections, we will firstly brief you through components of Docker, how we integrate Docker with testing tools, how we build and run our Docker, the possibility of incorporating Docker into our CI/CD, and finally, as we do with everything, monitoring and optimizing strategies. So in the world of containerization, Docker files are like the architects designing the blueprint for our testing infrastructure. So, what exactly is a Docker file? It's a script, a set of instructions, a recipe, if you will, that tells Docker how to build a container image. Think of it as a step by step guide to create a self contained environment for running. When we simplify the definition, we have to be aware of the key components of a Docker file. So let's quickly break them down. Every Docker file begins with selecting a base image. This is like choosing the foundation for your house. You might use an official image from Docker Hub like Node.js or Python as your starting point, depending on what you're working with. Next up, we set the working directory inside the container. This is where all the magic will happen. It's like moving into our testing lab. We then copy our application code, configuration files, and anything needed for testing into the container. This brings in all the instruments and tools required for our experiments. And then we install dependencies. Think of this as setting up our lab equipment. For example, if we're using Cypress for testing, we'd install its dependencies. At this stage, containers communicate through ports, so we expose the necessary ones. It's like creating windows into our lab, allowing the outside world to interact with our tests. And finally, we define the default command that will be executed when the container starts. This could be running our test suite or any other testing commands. In summary, Docker files are the architects of our containerized test environments. They allow us to create consistent, reproducible, and efficient testing environments, ensuring our tests run seamlessly, whether it's on our local machines or in the vast landscape of a CI/CD pipeline. Containerized test environments comprise Docker, Docker files, Docker Compose, and a diverse array of testing tools. And together they form a powerful ecosystem in the testing phase of software development. By adopting containerization, we do not only streamline testing processes, but also embrace a more collaborative and agile approach to delivering high quality software. And Aisha will now give us more context on the topic of integration.
Thank you, Rabina. So, integrating the testing tools with Docker is a game changer in modern software development. Docker allows you to encapsulate your application and their dependencies into lightweight containers, providing a consistent environment for testing. By incorporating testing tools into Docker, you gain the ability to create reproducible testing environments easily. This ensures that tests run consistently across various stages of your development pipeline. Docker's flexibility accommodates a variety of testing tools from unit testing frameworks to end-to-end testing suites. Imagine defining your testing environment in a Docker file, specifying the tools and configurations required. With a single command, you can build a Docker image that encapsulates your entire testing setup. This image becomes a portable and shareable entity, enabling team members to collaborate seamlessly. Docker Compose further enhances this integration by orchestrating multi-container setups, allowing you to include additional services or dependencies needed for comprehensive testing. Running tests within Docker containers provides several advantages. It promotes isolation, preventing interference between tests, and ensuring consistent results. It also facilitates parallel testing, enabling faster feedback on code changes. Integrating Docker into your continuous integration, continuous deployment CI/CD pipeline streamlines the automation of tests. Docker images can be seamlessly deployed across various environments, from development to production, ensuring that your application behaves consistently in different scenarios. Whether you're using popular testing frameworks like Selenium for web testing or Jest for JavaScript unit testing, Docker simplifies the setup and execution process. The result is a more efficient, scalable, and collaborative testing approach that aligns with the dynamic demands of modern software development. In essence, by marrying testing tools with Docker, you're not just testing code, you're testing it in a standardized, reproducible, and highly scalable manner.
In the world of continuous integration and delivery, this is where the rubber meets the road, and that is building our Docker images. So, the heart of our containerized test environment is the Docker file. As we've said, it's a script that guides the construction of our testing. Versioning is crucial at this part. It's like labeling each iteration of our laboratory setup. This ensures that we can recreate the exact environment when needed, promoting consistency across different stages of development. And for more complex applications, we can use multi-stage builds. This is like having different workstations for different phases of our experiments. It helps optimize the final size of our testing environment. And in real-world scenarios, multi-container setups are often used to deploy and manage applications with complex architectures. One common use case is a microservice-based architecture where different components of an application are deployed as separate containers, and each containerized service can be developed, deployed, and scaled independently. And to wrap it up, building and running containerized test environments is the backbone to efficient testing workflows.
Continuous integration and continuous deployment. The CI/CD pipelines are also crucial in today's software development practices, allowing for efficient and reliable delivery of software updates. Integrating Docker into CI/CD pipelines can further enhance these processes, providing benefits in terms of scalability, reproducibility, and deployment speed. By leveraging Docker, CI/CD pipelines can be easily scaled, allowing for parallel execution and multiple stages simultaneously. This scalability helps to reduce build and deployment times, enabling faster software delivery. In conventional CI/CD pipelines, managing dependencies and ensuring compatibility across different stages can be complex. Docker simplifies this by encapsulating both the application and its dependencies within the container. This allows for easier management of dependencies as they are bundled within the image itself, eliminating the need for manual installations or configuration changes in different stages.
And finally, we have arrived at the point of our brief, which is monitoring and optimizing strategies. And our favorite way to describe everything is analogy. So buckle up. So, just like a scientist constantly monitors and refines experiments, we too must keep a keen eye on our testing infrastructure. We must stress out the importance of monitoring. Monitoring is our microscope into the health of our containerized test environment. It's about gaining insights, identifying issues, and ensuring our tests run in a healthy and robust ecosystem. Tools like Prometheus, Grafana, and ElkStack become our observatory. They collect and visualize data, providing a real time view of container performance, resource usage, and the overall health of our testing infrastructure. And setting up alerts and notifications is key to having alarms in our lab. It ensures we're promptly informed when something goes bad, allowing us to address issues before they impact our testing pipeline. And when we talk about optimization strategies, scaling is our secret weapon. Containers can scale horizontally, allowing us to run tests in parallel and accelerate feedback loops. We can optimize our testing infrastructure to dynamically scale based on the demand. We should manage the life cycle of containers judiciously. We can start, stop, and remove containers when needed, avoid container sprawl, and consider using tools like Docker Compose to define and manage multi-container applications. And just like updating your equipment lab, regularly update your Docker images. This ensures you're benefiting from the latest features, bug fixes, and security patches, and it also contributes to the consistency and reliability of your testing environment. So, in conclusion, monitoring and optimizing our containerized test environments are the pillars of maintaining a healthy and efficient testing infrastructure. It's about ensuring our experiments run smoothly, providing reliable results in our journey towards continuous improvement.
And now, with all of that said, we've come to the fun part. Configuring Docker for testing involves creating a Dockerized environment that encapsulates your testing requirements. So the fun part is, of course, the demo. So in this demo, we will be using Cypress as a testing framework. It is JavaScript based and it stands out for its simplicity and power. It offers real-time browser preview, automatic waiting, and seamless integration. For the app that we will be testing, this is actually a little bit of a funny story, but we will actually be using a small app that Rabina developed in her college years, which sounds so far away right now, right? The app as an app is relatively simple, and for demo purposes, we have written down a couple of Cypress tests. So what we actually already done is we've created a Docker file that will build and run the application in a Docker container. And together with you, we will be developing a Docker file for containerized testing. We will be running the app on one container and running the tests on another.
I love that moment of somebody being unmuted. Okay, cool.
That moment, real quick. I just got so confused. Sorry about that.
It's all good. Okay, now Aisha, could you please open the VS Code and our application, which is written in Node.js Express? As Aisha mentioned, we wanted to drift away from using something open source in order to really demonstrate what it would look like when integrating Cypress with an existing project. So something to note for this demo, a prerequisite is to have Docker installed. Shocker, I know. And Aisha, could you please expand the app folder? This is where our application lives, and open up the Docker file so that we can review it together. Yes, we can see it, but you're muted.
Oh, sorry, I'm muted. Okay, so we have a Docker file that pretty much follows the basic constructions that we already talked about. Since this is the Node.js app, we will be using a pre-built Docker image called Node, and this number 20 that you see here is actually specifying the version of Node that we will be using. Next up, we need to set up the working directory of our app. Next up, we need to define the package JSON. Why? Because all of the dependencies of our app can be found inside the package JSON. And we need to copy that file also to our work there in order to be able to actually install all of the dependencies that we need and then later on start our app. So funny story, as you can see on the screen, we have two package JSONs and two package lock JSONs. The issue is that the Docker file that is inside the app folder only sees everything that is inside the app folder. So we had to make a copy of the package JSON inside the app folder. There is actually a solution for this, but we didn't want to overcomplicate stuff for now. So we just made a copy of it. There is a solution in creating a hierarchy and so on, but just a fact to be aware of. After we've moved also the package JSON to our we run the npm install, which will pretty much install all of our dependencies that we need. We copy all of that from that folder into our container. We need this line here can be a little bit confusing. So we need to expose a port so we can have access to our app that we will be running. We are setting the port to 3000. Essentially means that if the app is running, we will be able to access it on the on the Docker's port 3000. And finally, we need to define the command which will run the moment that our container has started. And for that, this will actually pretty much run our app, the npm run start. Before we start with everything else, let me just demo you how the app actually looks like and how to start it. So we need to get into the app folder and run the same command, which is npm run start. This will start the app on the port 3000. And it will open up somewhere in a tab that I will try to find right now. Okay, there we go. So this is Rabina's college project. It's a simple app. This is just a sign-in screen, but we just want you guys to see what are we actually working with. I will stop the app right now. And at this point, we have our base, we have our app, it's running, we have our base to incorporate Cypress.
Just a heads up, all rights reserved. This is my pride. Okay, now that we have something to test, let's incorporate Cypress to our project. In the terminal, Aisha, could you please type out the command npm install cypress dash dash save dash, and this will just provide us with the Cypress package. And we're gonna imagine some elevator music while this is going on. My least favorite part. Okay, thank God. Now that we have that, we can configure Cypress. And in order to do that, in the terminal, we write npx cypress open. This will just essentially spawn the Cypress app, and now we have to configure it. Let it just load for a sec. Please click on end-to-end testing, and this will just end-to-end testing. Maybe it's late on my end, never mind. So this screen contains the config files. We're just gonna accept these and click continue. And then we're gonna get a chance to select our browser of choice. For this demo, we'll be running in Chrome. And now we are able to create our first spec, which is essentially our first test. So Aisha, if you could click on create new spec, create spec. This is just a template in order to make sure that everything is running properly so that our configuration files are fine. So Aisha, yes, please click OK, run the spec. This is going to run that test. It's just going to navigate to a random Cypress IO page and make sure that it passes. Again, just for validating purposes to see that everything is set up fine. Now we can close both the browser and Cypress and navigate back to VS Code.
Okay, so this part that Rabina went through pretty much created a folder named Cypress with all of our needed components. The E2E folder means end-to-end folder contains our test, and we have a Cypress config. Yes, but for now it's pretty much empty. So our app will be running on one container, and it will be on port 3000. So our Cypress tests need to visit that port in order to validate the tests. So in order not to repeat the URL throughout our tests, we can define a base URL inside our config file just to eliminate the repetitiveness. So we will define the base URL here. We will put it to HTTP host, and we need a column. So when we start our app, it will run on localhost 3000, as we showed you before. It will be available on that port, but the tests will be in different container. And that container does not know what localhost means. This setup will pretty much not work. The keywords localhost should be replaced with hosts.docker.internal. We will do that right now because the Docker needs to look at our internal localhost. And we basically need to point this to our local machine since the app will be on our local machine, pretty much. This point here will make more sense as we move through the demo. It will make more sense pretty much later on as we explain and go through the ports and where the app is and where the tests are. So I'm just going to write down here host docker.internal, and just for our demo purposes, we've written down a couple of tests. We will just insert them here inside our spec.side.js.
Okay, awesome. Thank you, Aisha. So just a quick overview of this file. So we have the describe. It essentially contains all of our tests. So each if statement is actually a test that's going to be executed. And the reason why we've defined before all of these is if it weren't incorporated inside each of those if statements, we would have to tell Cypress to navigate to a URL. So again, just to avoid repetitiveness, we've said, hey, before each test, navigate to our local host in order to verify this. And then this backslash within visit is just a definition to visit the base URL. Okay, now that we have this out of the way, let's create our Docker file for Cypress. As we've mentioned, running the Docker file will create an image upon which the container will be built. So that's the general purpose. Thank you, Aisha, for creating it. First of all, as we've mentioned both in the brief and then Aisha explained the app Docker file that we have, we first have to define the base image. And this is just the image that we will be using, and the one that we will be using is from Docker Hub, which is already pre-built. So we type from Cypress / included colon 12.12.0. And the 12.12.0 is just the version that we will be using. After that, we are setting up our working directory. So we say work there /e2e. This is because our tests are defined there and they will be running in this working directory. And as we did previously, we have to copy the package JSON, which contains all the dependencies. So let's just wait for Aisha to type that out. And that would essentially allow us to run the two following commands, which is run npm install, which will essentially run all the dependencies within the package JSON. And then we run npm install Cypress in order to have Cypress available in our container. Once we're done, we will copy all of the code into the container itself. That is just with the copy dot dot. And finally, we define the command that will be executed when we start our Docker container. And that's cmd npm run Cypress run. Just wait for Aisha again, a bit of elevator music. Okay, now this command on its own will not work because we have not defined it. If you navigate, Aisha, please, to the package JSON. Within the package JSON, we have a section called scripts, and there you can define your custom commands. So we will define the one that we've provided within the Docker file. So we say Cypress run, that's what we told Docker to execute. And then we just provide what essentially it should do. If you look on the line above, there is like a custom start command that essentially starts our application by navigating to the bin folder and using Node. Okay, now we have the command to start our app, and that's pretty much it. Aisha, can you lead us to Docker Compose now, please?
Yeah. So right now at this point, we have two Docker files. One Docker file which is there to build and run our application, and another Docker file which is there to pretty much run our tests. So which means that we pretty much have a multi-container app here. And in order to orchestrate, because we need the containers pretty much together, we need to use Docker Compose to orchestrate the containers together. So we have to define our Docker Compose. It is a YAML file, and it will help us run the containers together. So I will create a new file. It's called Docker Compose.yaml. So the other Docker files are a blue whale. This one is a pink whale. So let's remember the versioning that we talked about. So first, for Docker Compose, first let's define the version. So for version, we can put one first version, hopefully the last one. And now, since it's a Docker Compose, means it's multi-containers, multi-services pretty much. So we need to define which services to start. So the first one is app. So we define which services to start. And the first one, let's define it as app1. And we need to know from where to build the Docker image in order to start the container. So we need build, and there we need to put the context. So from where will we be taking that something that we need to use as a guideline for creating that image and a container? So we provided a context. So pretty much we provided the Docker file, which you already saw. It has a list what we need to do before everything is started. So the context for app is the Docker file inside the app folder. So we need to just say, okay, the context for this is inside the app folder. And that is where the Docker file is, and it will help us build the image. And another thing, so remember now that port 3000 that we talked about, we need to open ports. So the command that we put in the Docker file, which is expose 3000, basically exposes port 3000 on our container. We need a port pretty much on our side, which will communicate with that port and which will display what is on that port from our container. So in order just not to make this confusing or something like that, we will put we will put also 3000. This means that our port, local port 3000, will display whatever we have on our container on port 3000. And that is pretty much for the app part. So we need the Cypress part now. And I keep writing Stupress from, of course, no apparent reason. Sorry about that. So, of course, as we did for the app, we need to tell it where to build from. And this Docker file is actually in the main folder. So we just need to put the path where this is. And another thing we must define. So in order for us to run the application on one container and then run our tests on another container to hit the app that is in the first container, we cannot build these two simultaneously. They cannot start simultaneously. We have to have app running before we start the Cypress container. So we have to add something that will stop this container from creating before until the app container creates. So we can do that with a simple line, which is depends on, and we will say it depends on app. So we this will build both images and make sure that the Cypress container depends on the app one, because we need the app to run in order to run the tests. And this pretty much is a very small file. It concludes the setup that we need. Rabina, drive us further.
Thank you, Aisha, for setting up the app and the Supras containers. The only thing left to do, essentially, because we do have our Docker Compose, is to execute our Docker Compose and see that we've successfully created our containerized test environment. So, Aisha, could you please open up the terminal? It's already up, good. And write out the command Docker Compose build. This will essentially both spawn up our Docker Compose and build the images in it. So what this does is it starts the composer, but it first builds the images based on our Docker files, and then it will create two separate containers using those two images. So Aisha has Docker here right now. It's just going to visualize everything that's going on in the background. As you can see by the terminal, it's still actually building the images. And as you can see, we have our first one. Yay. We're just waiting for the second image to build, and that's going to provide us the setup for both of our containers. Again, elevator music in the background. As we wait for this, npm install is the longest one, I swear. So once that is done, it's going to be smooth sailing from there. We'll have one.
I swear we had like a mental breakdown every time we had to wait for this run npm install.
Oh, the good part is that if you do like slight updates on your code or in the definitions of like Docker files or Docker Compose, and you don't really mess with like the packages, most of this gets cached. So the next time that you run it, if you want to change something, add an additional Docker file, Docker file, maybe you want an additional container. But yeah, anything that you do afterwards, most of this does get cached. So it's super quick, but since we're doing it from scratch, you have to suffer with us. And we have to wait for the npm to install.
This one is long. I don't know why. I think app. Oh, there we go. App was faster for some reason.
I really hope that like that monologue of mine would be enough without it being cached.
Well, you cannot monologue enough, it seems.
Okay, they're created. Yay. You can see in the terminal, they're created. We can see in Docker that they're created. And then I used to navigate to containers. Thank you. We can see our Docker Compose. And then within the Docker Compose, we have both of our containers up and running right now. They're not really doing anything, but soon enough, our Cypress will execute test cases. And Aisha, maybe you could just minimize the Docker so they can see the terminal, because that's where or you can open up the logs later on. It doesn't really matter. So our app started. Aisha already said we've defined in the Docker Compose that our app has to start in order for Cypress to run. So now we're just waiting for Cypress to run its test cases and provide us with the results. And as you can see, all of our tests passed. Yay. You could also look at all of these within the Docker itself. It's much neater than the terminal, but I think terminal is mostly used. Maybe Aisha could just show them the logs. So again, just a copy of the terminal. And as you can see, if you navigate back, thank you, Aisha, Cypress is shut down because we've essentially told it just to run the test cases. It did that and it exited, but our app is still up and running if we need to use it. And again, as Aisha said, because we declared the ports, we can navigate to localhost and it will still be there. That would pretty much conclude our demo of setting up a containerized test environment.
Another look at Raba's application.
Yes, yes, please. It's very responsive.
But yeah, that pretty much concludes our demo. I hope all of you enjoyed this and enjoyed geeking out with us over containerized test environments.